First task, we have two functions. First function is x plus y for real numbers, and is this function is one-to-one? Yes, it's not one-to-one because we have two different inputs and same outputs. And second function is x multiplied by y, and it's also not one-to-one because we have same inputs, different inputs as the same outputs. And both of this function is onto because for first we can choose every random number z and 0, and it will be onto. And for x multiplied by y, you can choose every number z and multiply by 1, and it will be onto. Next task is we have function x squared plus 2, and for integers we have a not one-to-one because we have a same input, same output for different inputs. For example, minus 2 and 2 is equals to 6, and it's also quadratic function. And this function will be always greater than 2, so for all x that are integers, so it's not onto. And for a as natural numbers, here we can find a vertex by this formula, and as we can see is one-to-one because we take only one part of parabola, so it's one-to-one. And it's not onto because here we can input 1, 2 and 3, and we don't get 1, 2 and 5 as outputs. And next task, we have this function x squared plus 14x minus 51, and here for every natural number and b integer greater than minus 100, we find a vertex, and it's minus 7 is minus 100, and it's one-to-one because also here we take one part of a parabola. It's not symmetric, and it's not onto because we don't have values for minus 100 and minus 36, between minus 100 and minus 36, because for example, if we input 1, that's a lowest natural number, we get minus 36, so it's not onto. Here it's also not one-to-one, and here is onto because we have values for this numbers, we have values. Next, we have a function 2n plus 3m for natural numbers, and it's not one-to-one because we have same outputs, and it's also greater common divider for this function is 1, so it will be onto and not onto. For real numbers is the same because great common divisor is 1, nothing changed. Next is a 14n plus 22m for natural numbers, and as we can see, we can get similar numbers because greater common divisor is greater than 1, and it's not one-to-one because of that. And when we have two even numbers, it only can give us even numbers and not odd. Because of that, it's onto because we can get odd numbers. Same here, great common divisor is 1, so it's not one-to-one and onto. Here we have two sets x and y, and we can create one-to-one functions. Here is two examples of two functions, so we can get 24 combinations of that. And from y to x, one-to-one is impossible because there is more elements in y than in x, and more elements means that in domain we have more elements than in codomain, and that's impossible. So 0 combination for this. And next we need to check how many onto functions we can create for x to y. It's impossible because there is more elements in y set than in x. So yes, and last, from y to x there is 36 combinations by arithmetic formula.
In problem 4, we have function that has range from 0 to infinity, and when we input it, the output will be from minus infinity to 0. So the function is minus x underscore. If we suppose that if of x is y, then to take inverse, we suppose that x is f of y, and it's equal to minus square root of y. So by squaring two sides, we get y equal to x squared. And when we inputted positive numbers and got minus numbers, because we have here minus, and for the inverse function to be true, we should get the positive numbers, so it satisfies these conditions. So in 10th problem, here we have set of sets s and t. So function f maps s to t, and g maps s to s. So that's our f function and g function, and f the composition of f of g will be look like this, and it's defined. However, g of f composition will be undefined because the f function maps to t, however g function maps only to s. So some of the numbers inputs are not the same, so we can get this composition, so it's undefined, as well as f composition to f, and g of composition to f is defined because the s maps to itself. And if we answer to the b section, the f will be 1-to-1, not onto, because it has the values. So we can say that the f is 1-to-1 because it has unique values for every y, no duplicates in outputs. So it's also onto because for every y, which are mapped to our t, there is a value in x. So g is not onto and not 1-to-1 because it has duplicates. For example, if we input 1, 2, and 5, we get same output. But it's also not onto because some of the values are not included. For example, we have no x mapped to our 4 value, and we have no x for our 5 value. So we could say that f is bijection, and it has inverse function whether the g is not bijection, has no inverses. So in this problem we should find the compositions, So in order to find compositions, we should look at this function and take it as x of this function. So if we apply it, the x plus 1 will go there and we get this function. For this one, we look at this function and take it as x for this function, and this we get in the end 1 over 1 plus x. And for this one, like other ones, we get this and input for the h of x and get the 2x plus 1 over x. And for the last one, we found j composition x, and it was 1 over x1, and input it as the x of f, and at the end we get 1 over x plus 2. So if our f function maps a to b and g function map b to c, and suppose that this composition is 1 to 1, f is onto, we should explain why j can be 1 to 1. So if g of f of x1 is equal to g of f of x2, it means that x1 and x2 should be the same, and we take this as the y1 and this as the y2, so there must be a y and y1 y2 exist in b set. So f is onto, so that means that there is every y in b there is x in a, such that fx is equal to y, and this means g of y1 is equal to g of y2, and this gets us to the point that they are equal, so g must be 1 to 1. And in this one, we suppose this composition is onto, this composition is 1 to 1, and this is this should be onto. So this means that there must be, for every c in set C, exists an a in set A. So for b1 and b2 existing in b set, if g of b1 is equal to g of b2, must be b1 equal to b2. So every b for existing in b set exists an a in a set, meaning that f of a must be b. So in order to explain and prove this one is onto, we should think otherwise. If we assume that the f is not onto, so this means that some b0 in b has no a in a, that satisfies this condition. F of a is equal to b0. So since b0 is a match of f, there's no a in a that maps to it, so no a in set A of the composition g of f of a equal to g of f of b, and g of b o doesn't exist an image of this composition. But this contradicts the assumption that g of f composition is onto, because it's supposed to get every value in C, and g of b0 in existing in C set, since the b0 is in B set and g is the maps b to C, so this must be onto. So let f map a to B set and g b to C set, and this is 1 to 1. G of f of x1 is equal to g of f of x2. Since g is 1 to 1, then f of x1 and f of x2 are equal, f is 1 to 1. We look into this, and x1 is equal to x2. So this means g of x, g of f of x is also 1 to 1, meaning this injection. F of x is equal to 0 for every x in the set it's not 1 to 1, so g of y is equal to y squared, which is 1 to 1 on non-negative values. So g of f1 we get 0, g of 0 is 0, g of f2 is also 0, and we get 0. So this composition is constant, not 1 to 1, so the converse fails. So g of f of x is 1 to for every c value existing in C set, such that for every a value existing in A, such that g of f of a is equal to c, meaning that p of f of a that exists in B set, so g of b is equal to c. So for every c value in C set corresponding to corresponding b in B set, g of b is equal to c. So this composition is onto. F of a gives valid input to our g function, and g is onto.
Chapter 3 and Section 3, task number 5a. Proves that the function g is 1 to 1 and onto. For given us function n to z is 1 to 1 and onto. The function g n to z is defined by g m n equal to m function n. We need to prove that g is both 1 to 1 and onto. For first proof 1 to 1, we need to show that for any two pairs m1 and 1 and m2 and 2, if g m1 and 1 equal to g m2 and 2, then m1 and 1 equal to m2 and 2. From the definition of g, we know that g m1 and 1 equal to m1 fn1. G m1 and 1 equal to m1 f and 1, and g m2 and 2 equal to m2 f and 2. If g m1 and 1 and g m1 and m2 and 2, then we describe that f and 1 equal m2 f and 2. This implies that m1 equal to m2 and f and 1 equal to f and 2. Since if f is 1 to 1, we have n1 equal to n2. Therefore, m1 and 1 and m2 and 2, providing that g is injective. m1 and 1 equal m2 and 2 is 1 to 1 function. Second proof is onto function. We need to show that for every pair m and z and z. There exists is a pair m and n and 2n such that g m n equal to m z. From the definition of G, we know that G m n equal to m f n. For a given m and z, we need to find m and n such that m equal to m and fn equal to z. Since f is on top for any z, there exists an n to n such that fn equal to z. Therefore, we can choose m equal to m such that fn equal to z, ensuring that gmn equal to mz. This proves that G is onto. Since G is both injective and surjective or one-to-one and onto, we conclude that G is onto. That Gmn equal to mz. It is a final conclusion that proves that G is answer. G is onto. In this part also is that f is one-to-one function. Task number 5b. One-to-one corresponds between n to n and n to z. Our goal is we need to find a one-to-one correspondence between the sets n to n and n to z. Solution. Understanding the sets, Nn is a set of ordered pairs. It is ordered pairs of natural numbers. N to z is a set of ordered pairs with the first element is a natural number and the second element is an integer. Construction Z by Jackson. We need to create a function h n to n to n to z that pairs each element n to n with an element n to z is a one-to-one manner. A natural way to establish this correspondence is to map the second component of the pair n to n to an integer z. For example, map the second component n to n for n to fn, where fn is an injective and surjective function from n to z. A common such function is fn, for example, n over 2 minus n plus 1 over 2. If n is even, if n is odd. This function maps natural numbers to integers, ensuring that the pair mfn creates a one-to-one correspondence between n to n and n to z. In conclusion, I want to say that by using the function f, we can establish a bijection between n to n and n to z, satisfying the requirement for a one-to-one correspondence. 12a. Proving that the intervals 0 to 1 and 1 to 2 have the same cardinality. Our goal is we need to show that the intervals 0 to 1 and 0 to 2 have the same cardinality, meaning that there exists a one-to-one and onto function between the two intervals. For construction the bijection, to demonstrate that the intervals have the same cardinality, we can create a function f 2, 1 to 2. that is both one-to-one and onto. One such function is a linear transformation fx equal to x plus 1. This function takes any number x, 0 and 1, and maps it to fx equal to 1 to 2. We define the bijection. Firstly, 1 to 1. If fx1 equal to fx2, then x1 plus 1, x2 plus 1, we have a x1 equal to x2. It is a one-to-one function. Second one is onto. For any y equal to 1 to 2, we can find at x 0 to 1 such that fx equal to y. Specifically, x equal to y minus 1, since y have a 1 to 2, it follows that x equal to 0 to 1. Since the function is both one-to-one and onto function, it is a bijection, and thus the intervals 0 to 1 and 1 to 2 have the same cardinality. Second one is B, proving that intervals 0 to 1 and 4 to 6 have the same cardinality. Our goal is we need to prove that these intervals have the same cardinality. Our solution is create the bijection. To show that these cardinalities have the same cardinality, we can construct a linear transformation function f 0 to 1, 2, 4, 6. The function is fx equal to 2x plus 4. We'll map that x 0 to 1 to fx equal to 4, 6. We define the bijection. Firstly, 1 to 1. If fx1 equal to fx2, then 2x1 plus 4 equal to 2x2 plus 4, which simplifies to x1 equal to x2. Therefore, the function is 1 to 1. Second one is onto. For any y equal to 4, 6, there exists an x equal to y minus 4 over 2 equal to 0. Since y 4, 6, it follows that x 0 to 1. This proves that if f is bijection, so the intervals 0 to 1 and 4 to 6 have the same cardinality. Task number 12, C. Proving that any two open intervals a, b, and c, d have the same cardinality. Our goal is we need to prove that any two open intervals a, b, and c, d have the same cardinality. Our solution is generalizing this approach. The general approach for any two open intervals a, b, and c, d is to construct a linear transformation that maps any point x equal to ab and to point in cd. The function is fx equal to d minus c multiply x minus a over b minus a plus c. We'll map that x ab to fx c d. We define the bijection. Firstly, 1 to 1. If fx1 equal to fx2, then d minus c multiply x1 minus a over b minus 1 plus c equal to d minus c multiply x2 minus a over 2b minus a plus c, which simplifies to that x1 equal to x2 onto. For any y equal to cd, we can find x equal to y minus c multiply b minus a over d minus c such plus a, such that fx equal to y. Since y cd, it follows that x equal to ab. Since the function is both one-to-one and onto function, it is a bijection, and that intervals AB and CD have the same cardinality. Final summary for this task: for part A, construct a linear transformation fx equal to x plus 1 to show that the intervals 0 to 1 and 1 to 0 have the same cardinality, and other parts have the same cardinality. The last one task is 20a. The set of x, set of r, set 1, x2. The solution, the set consists of real numbers between 1 to 2. Is exclusive. The real numbers between any two distinct real numbers from an uncountably infinite set, meaning that there is no way to list all the numbers is interval in a sequence that can be mapped to the natural numbers. Uncountable. The set of real numbers between 1 to 2 is uncountable because it cannot be put into one-to-one correspondence with the natural numbers. Are there infinitely many real numbers between any two given numbers? In conclusion, final answer is uncountable. Uncountable. Second, B. We have a x, a set of q, 1 to x, y, z. Our solution is this set consists of all rational numbers between 1 to 2. The rational numbers, while infinite, are countable. Infinite. We can list these rational numbers between 1 to 2 in a sequence, meaning there is one-to-one correspondence between the set and natural numbers. Justification: countable infinite. Countable infinite. The set of rational numbers between any two real numbers such 1 and 2 is countable because the rational numbers themselves are countable. They can be listed in a sequence. In conclusion, final answer is countable infinite. Next one. C. M over to n, m set of n, set of n, m less than 105, n 105. Our solution is a set consists of rational numbers m2 over n, where m and m are natural numbers. M is less than 100 and n lies between 5 and 105. Since m has 29 possible values from 1 to 99, and n has possible 99 possible values from 6 to 104. The number of possible distinct fractions is infinite. Justification: finite. The set of is finite because m and n are taken from infinite sets, and the number of distinct elements in the set is finite. 99 choices from for m and 99 choices for n. And in conclusion, answer is finite function. The second one is D. We have the set m over 2n, m is the set of z, n the set of z, m less than 100, 5, and 105 the set of over. The set consists of rational numbers m to n, where m and n integers. M less than 100 and lies between 5 and 105. The set is finite because m has 199 possible values from -91 and to 99, and n has 99 possible values from 6 to 104. Justification: finite. The number of possible distinct fractions is finite because both m and n come from finite sets. Our answer is finite. And next, E. We have a set A plus bi, a, b, a set of n. Our solution: this set consists of complex numbers form of a plus bi, where both a and b are natural numbers. There are infinitely many possible values for any a and b. Each unique pair a and b produce set is unique complex numbers. Therefore, the set is countable infinite. Justification: countable infinite, since a and b can each take infinitely many natural numbers values, and the set is product is of two countably infinite sets. It is a countable infinite. And our conclusion answer is countably infinite. Next one, F. We have a set of A, B, the set of Q, A plus B equal to 1. Our solution: this set consists of pairs of rational numbers A and B, such their sum equals to 1. For any rational number A, we can find a corresponding by b equal to 1 minus a, which is also rational. Since the rational numbers are countable infinite, the set is countable infinite. Justification: countable infinite. The set consists of rational numbers that satisfy a linear equation, and since the rationals are countable infinite, the set is also countable infinite. And our answer is countable infinite. And the last one is G. We have a set AB, the set of R to R, when B equal to n minus e quadratic in the set. Our solution: this set describes the upper half of the unit circle in the Cartesian plane. The condition B equal to 1 minus a quadratic over this means that for every a in the set of -1 to 1, there is corresponding that also B has these cardinalities. Since there are infinitely many real numbers between -1 to 1, the set is uncountable. Justification: uncountable is the set is continuous and corresponds to the upper half of the unit circle, which contains an uncountable infinite number of points. There is no way to list all the points in the set in the sequence. And our conclusion answer is uncountable. Uncountable.
In the first exercise, we need to determine is the function is one-to-one. One-to-one function is the function where for each y we have unique x. So in the first exercise, if we take 1 and 2 and 2 and 1, we have the same result. So because of that, the function isn't one-to-one. In second exercise, we also need to determine if the function is one-to-one, but also we need to check onto function. So first of all, we need to make an equation with x1 and x2, open the brackets, and we see that in the second bracket it can be equal to 0. So only first bracket can equal to 0, and we have that x1 minus x2 is equal to 0, and so x1 is equal to x2. Because of that, the function is one-to-one. If we need to determine if the function is onto, we need to know that for each y there exists x unique. So if we take in our equation y equal to 1, we can't find x, so the function isn't onto. In the 15th exercise, we need to determine if the function is infinity, countable or uncountable, or this function is infinity. So in the A, we have xy equal to 1 and xy is integers. We can put 1 to x and 1 to y. We have first answer, and the second answer is -1 and -1. So because of that, because there's only two answers, it's finite function. In B, we have xy is rational numbers and xy also equal to 1. We can write that y is equal 1 over x. So because xy is rational numbers, is uncountable infinity. In C, we have x is rational numbers. 2x minus y is equal to 6. So we can write that x equal to y plus 6 over 2. So because of our x is rational number, is the function is countable infinity. In Z, we have x is rational number, x equal to py. So because of y is integer number, this function is countable infinity. In E, we see that x is rational number, x squared plus 8 is equal to 0. So we can write that x squared equal to -8. So because of that, we can exist x. So the function is finity because we have only 0 elements. In F, we have integer, natural, and rational number. So integer is countable infinity, natural also, and rational number is countable infinity too. So we can make a conclusion that its all function is countable infinity.